First, I want to thank the organizers for inviting me. It's very nice to be back. Oh, I can
Sorry.
That's not on my end, right?
No, I
Anyways, so today I'm not going to give a quantum computing talk. I'm going to give a quantum simulation talk. It's work that I started 2 summers ago when I was an intern here in collaboration with QERA. And the goal of the project was to just try to see what types of interesting many-body physics can we probe using QERA's publicly accessible quantum simulator. So the plan for the talk is, first, I need to give some background. I'll begin by giving a crash course on how Rydberg atoms work, since that's the building block for their quantum simulator. Then I'll give some brief details about the capabilities of their simulator. Then I'll cover the background, some of the work that's been done before, studying many-body physics using these Rydberg atom arrays and quantum simulators. And then I'll talk about maybe what's missing from that field. Then I'll present the results that we came up with, where we were trying to fill in some of these gaps in what's been done in this field. Okay, so Rydberg atoms are an ideal 2-level system. They consist of the ground state and an excited Rydberg state of an atom. The important properties of the Rydberg state are that 1, it's stable, it has a long lifetime, and 2, it has a very high principal number, so it's high energy, it has a very large spatial extent. That's the green atom there. That green circle is supposed to show the spatial extent of that orbital. The way that we typically interact with these things in experiments is we shine laser light on them. We tune that laser light to the transition frequency between the ground and the excited states. That is this term in the Hamiltonian, where omega is what we call a Rabi drive, which is the amplitude of that laser light. And it just drives transitions between G, the ground state, and R, the Rydberg state. We can also detune that laser away from the proper frequency. And what that does is it shifts the energy of the Rydberg state relative to the ground state. That's captured by this term in the Hamiltonian, where n is just the number operator for the Rydberg state. And the interesting many-body physics shows up when we have, of course, multiple of these Rydberg atoms. Because the Rydberg state is very extended, there's a van der Waals interaction between neighboring Rydberg excitations that manifests as this 1/r⁶ density-density interaction. The important consequence of this is something called the Rydberg blockade, which is a phenomenon where neighboring Rydberg excitations or neighboring atoms prevent each other from being simultaneously excited into the Rydberg state, because if they're too close, this 1/r⁶ blows up and it just becomes energetically and unfavorable for them to simultaneously excite. So what we're going to see is that there's this competition between the detuning, which maybe wants to populate a lot of Rydberg excitations, and this blockade phenomenon that prevents them from happening simultaneously. Okay, so now a crash course or a primer on what QERA's Aquila device is capable of. It's a quantum simulator that I guess I'll just go through how it works. So the first step is to load up to 256 Rydberg atoms into an array of optical tweezers, which then those optical tweezers rearrange themselves into a user-defined geometry. So in this picture on the left, that's the starting grid with the atoms loaded into it randomly, and then the tweezers are rearranged into a square lattice in the middle. Then the tweezers are released and the atoms are allowed to evolve under a user-defined profile for the driving fields, which is basically just telling the system what the Hamiltonian is. And then after it evolves for some amount of time, then you measure it through this fluorescence technique where the ground state lights up because you can do the fluorescence out of the ground state, but the Rydberg state is invisible. And so in this picture, the green dots are ground state atoms and the red dots are Rydberg excitations. Okay, so now I want to move on to some background of what types of many-body physics people have studied in these types of systems. The simplest array that you can construct is just a square lattice array. This phase diagram in the bottom left is from a work from 2020 where the authors did a DMRG study of what types of phases will show up in a square lattice of Rydberg atoms. The x-axis is the detuning in the system. So larger detuning on the right means that there's a lot of, there's an energetic benefit to having a lot of Rydberg excitations. And the vertical axis is the Rydberg blockade radius. So the higher that is, the more that these Rydberg excitations will prevent other Rydberg excitations from showing up. There's a number of different phases in this phase diagram. On the left, this entire band is a disordered phase where there's a low density of Rydberg excitations that just sort of homogeneously fill in the system. But when we turn delta up, these excitations try to form a high density, but then they kind of interact with each other and form these density ordered phases. So this bottom left phase forms a checkerboard pattern, where here dark green indicates a ground state atom and yellow is a excited Rydberg state. And what they're doing is that this Rydberg blockade is preventing nearest neighbors from being simultaneously excited. We go up a little bit, there's a thin stripe of something called a striated phase that shows up, where the radius at which the Rydberg excitations are blockading each other increases. So now the lattice of that pattern, or the lattice constant of that pattern, increases. We go up again, there's something called the star phase, where they form a slightly more complicated arrangement of excitations. Importantly, shortly after this paper came out, there was an experiment done at Harvard where they constructed the 16 by 16 array of atoms and tried to prepare these phases, and they were successful. So in each of these pictures, like I said before, the green dots are ground state atoms and the red circles are Rydberg excitations. And they were able to design adiabatic state preparation protocols to create each of these phases. So I'm calling them phases, but really this is kind of just a clump of atoms. And it's not very convincing on its own to just see these patterns of densities and call it a phase. What would really be convincing to show that this is truly like a quantum phase of matter is to look at the universal scaling that emerges at phase transitions of these states. And amazingly, they were able to get very good proof of a universal scaling at phase transitions. So I don't need to go into the details of this, but the sort of hallmark of universal scaling is this phenomenon called data collapse, where you repeat an experiment with different parameters and then rescale the results you get at different parameters. And if it's truly a phase transition, you should see all of that data collapse into a single line. And that's exactly what's happening in these two plots here. And amazingly, the critical exponent, which is just the parameter for this data collapse that they used to accomplish this with their data, matches extremely well to what was theoretically predicted. And this is one of I think it's the first realization of the D2 Eisenklasser universality class phase transition that's been seen in an experiment. So they really did construct these quantum phases of matter on their quantum simulator. The next more interesting thing that we could study, and then another slightly more complicated lattice, would be the Kagome lattice shown here. In a similar paper by the same group, they showed with DMRG calculations that they also get these density ordered phases where they break translation symmetry. In this plot now, red means it's a ground state atom and green means a Rydberg state. But they also found the more complicated things, such as this thematic phase where translation symmetry is preserved by the state, but rotation symmetry is broken because in each of those unit cells, one of the three sites of the triangle gets picked out, so it's breaking rotation symmetry. And then there's also a phase that they found in between those two that's sort of mysterious. They didn't really work out exactly what it was, but they have evidence that it's some sort of strongly entangled liquid in that part of the phase diagram. And I'll get back to that in a couple of slides. And the last bit of background I want to talk about was a very cool experiment that, again, the same group did a couple of years later. Actually, that's the same year. Things move fast. And this was an experiment where they built, instead of a square or a Kagome lattice, they put the atoms onto a ruby lattice. And they found some of the first strong evidence for the presence of a Z2 quantum spin liquid, or the Torr code. Okay, so a lot of interesting things have been done studying physics in arrays of Rydberg atoms, but there's also a lot of things that are missing. One thing is this phenomenon of multicriticality, which has two different important aspects to it. First is the presence of multi-component order parameters. So the order parameter is what describes the physics of, or describes the property of the phase. And all the things I talked about previously have just a single component in their order parameter. But when you have more complex patterns of symmetry breaking, more complex physics happening, you can have multiple components in your order parameter that transform differently under the broken symmetry. So this is something that we'd like to be able to see in quantum simulators. Another thing that hasn't been seen so far are multi-critical points in the phase diagram where where three or more phases come together at a single point in the phase diagram. And the physics associated with those phase transitions are more interesting than what has been seen so far in the previous experiments that I talked about, which really are just coming from the physics of very simple toy models. Another thing that we'd like to be able to see is a quantum analog of the water vapor transition. So the water vapor transition is characterized by having a first order transition across this line in this picture between the water and vapor phase that terminates at a critical point, which means that you can sort of evade that phase transition and go around it and continuously transition between the two phases. This has relevance in quantum environments as well. For example, it shows up in the high energy context in this phase diagram for the condensation of the Higgs field. And so it would be really nice if we could have a tabletop experiment where we can access a quantum analog of this water vapor transition. And then finally, I want to get back to that mysterious entangled liquid phase that I talked about before. In a follow-up paper, those authors did a quantum Monte Carlo study of that phase, and they found evidence that it exhibits emergent glassy dynamics, where things decay in a much slower fashion than you would expect. But because it was a quantum Monte Carlo study, they were only studying it in imaginary time, and it's much harder to access real-time glassy dynamics computationally. And so another thing that we hope to see is some evidence of this emergent glassy dynamics in an experiment on Aquila, which is QARA's quantum simulator. I can't remember if I said that yet. Okay, so our strategy for studying these things is to, instead of starting with something simple like the square lattice, we need to use a lattice that has more structure. And the lattice that we'll use today is the Lieb lattice, which you can get by just taking out the center of each of these plaquettes of the square lattice. The important change that happens when you do this is that now you have much more structure in your unit cell. So you have the A sublattice, which is a high symmetry site that has all the same symmetries as the square lattice, but then you also have these B and C sublattice sites that are lower symmetry because they only have C2 and inversion symmetries instead of having the full four-fold rotation symmetry that you have in the square lattice. Another nice thing about this Lieb lattice is that you can skew it and turn it into the Kagome lattice, which is the platform in which they saw evidence for this emergent glassy dynamics. So we're hopeful that in the Lieb lattice, we can also see that emergent glassy dynamics. Okay, so first I need to present the numerics that we did. So this is a phase diagram for the Lieb lattice that I calculated using DMRG employed on Perlmutter in the basement when I was an intern here. So the axes are, the horizontal axis is the detuning, and the vertical axis is the Rydberg blockade radius. The color comes from the entanglement entropy, which doesn't really matter what that is specifically for the context of this, but sudden changes in the entanglement entropy indicate boundaries between different phases. So we have 4 phases showing up in this phase diagram. On the left is the same disordered phase that we saw in all the other ones, where there's just a low density of homogenously spaced Rydberg excitations. In the bottom right, we see what we call the symmetric phase. We call it symmetric because it doesn't really break any symmetries, but the Rydberg excitations all sit on the B and C low symmetry sublattices, and the A sublattice is dark. If we go up in the phase diagram, we get to another phase that we call a collinear phase because the atoms or the excitations form these stripes. This phase breaks the C4 symmetry of the lattice, so it's more of a phase in the traditional sense. And yes, I think that's all I wanted to say about that. And then if we go up once more, we see the star phase where the excitations form this more complicated pattern on the lattice. If you're paying close attention, you'll notice that all 3 of these phases also showed up on the square lattice, so you might be thinking, what's interesting about it? But the important thing is that because we have this extra structure in the unit cell of the lattice, these phases actually exhibit a very distinct pattern of spontaneous symmetry breaking compared to what we saw on the square lattice. So for example, this star phase, unlike on the square lattice, there's 4 distinct ways that we can arrange it on the Lieb lattice, which are shown with these in these 4 different diagrams. We can combine these different patterns into 2 different order parameters that characterize the phase. One of them is a single component, psi3, that transforms under some irreducible representation of the symmetry that was broken. And then we also have this 2-component order parameter that transforms under a different irreducible representation. And so this is exactly one of those multi-critical phenomenon that we wanted to see. We've been able to, by transitioning from the square lattice to the Lieb lattice, we engineered a star phase that now has a multi-component order parameter instead. Now, if we go back to the collinear phase, I forgot to mention, the star phase, it not only breaks the C4 symmetry of the lattice, but it also breaks some of the translation symmetry of the lattice. Unlike the collinear phase, which preserves that translation symmetry. What that means is that when we go from the disordered phase to the star phase, we have a first order transition because we're breaking all of the symmetries at once. But we can take a different path into the star phase by cutting through the collinear phase, where we first break the C4 rotation symmetry, and then we break the translation symmetry later. And what this tells us is that going through disordered to collinear to star, we have to pass through 2 second order transitions. But if we go straight from disordered to star, we can go through a first order transition. So this requires them to meet at a tricritical point in the phase diagram. And this was the other aspect of multicritical phase transitions that we wanted to access. So we have strong numerical evidence that we're seeing the multicritical phenomenon that we were interested in. But the question is, can we put this onto Aquila and actually see anything? So to do that, there's 2 problems. One is that we can't build a cylinder like we use in DMRG. So we have to use an open lattice like this. And the other problem is that we can't measure entanglement entropy on the device. So this picture is still numerics. This is the entanglement entropy calculated on this open lattice. And rather than look at entanglement entropy on the device, we just have to measure order parameters for the different phases and see how well they match up with the order parameters that we calculate from the numerics. And what we find is extremely good, not only qualitative, but also quantitative agreement between the numerics and the simulations on the device. So in these plots, the right is from numerical simulation using DMRG, and the left is a measurement from a set of experiments on Aquila. And you can see that the order parameter shows up in the same region, but also has a very similar magnitude to what's predicted numerically. So that was very exciting to see. We had the same thing happen for the collinear phase. And the same thing happened for the star phase, although the star phase is slightly less convincing because it has a larger unit cell, so the effective system size that we were able to access on the device is lower. But the important thing that we've shown here is that we can get very good agreement between experiment and simulation, and this means that we are able to access this, well, maybe not at this scale, but in the very near future, we'll be able to access the multicritical phenomenon predicted for this system if we can increase the system size by a few times, which is very much within the roadmap that Guerra is aiming for. Okay, so the next thing that we wanted to see was this analog of the water vapor transition. So the important thing that happens in that transition classically is that the density of water changes abruptly across that first order transition. We can think about something similar happening on the Lieb lattice with Rydberg excitations if we start in the symmetric phase. What we would want to see happen is that we want to have the excitations move from the B and C sublattice onto the A sublattice. Since we're going from having 2 sites lit up to 1 site lit up per unit cell, this would be an abrupt change in the density. We can access this by locally changing the detuning on these B and C sublattices. And this is a capability that was recently added to Aquila. So this is something that we can access experimentally as well. To do the numerics, we again are using a lattice that we can actually implement on the device. So it's not a cylinder, so it's different from traditional DMRG studies. This is the phase diagram that we found numerically, where the horizontal axis is the global detuning, and the vertical axis is the local detuning that's only put on these B and C sublattices. And what we see is very similar to what you get in the water vapor transition, where there's a very sharp critical or very sharp phase transition happening here that terminates into this very broad feature. It's more clear what's going on if I, instead of plotting the entanglement entropy, I plot the sublattice magnetization, which is just the density on the B and C subsites minus the density on the A subsite. We can see clearly that there's a first order transition where the density abruptly switches from B to C as we go across it, but it terminates and we can do a crossover if we go around that point. So this is exactly the analog of the water vapor transition that we wanted to see, at least numerically. And we can see that density change happen. Visually, if we just plot going from top to bottom and left to right here, you can see that the BC sublattice is lit up on the left too, and the A sublattice is lit up on the right too. So we have this first order transition. If we want to try to prepare these states on the device, we have to be very careful because the preparation protocol that we use needs to avoid this first order transition if we want to have a very well prepared state. To avoid it, what we do is we use 2 different preparation protocols. One, we increase the local detuning first and then the global detuning next, which is just indicated by these arrows. Or we can also do the global detuning first and then the local detuning second. And depending on where the point is that we're trying to get to, one of these 2 paths will work well, and one of them will intersect with that phase transition, which will sort of scramble things and give us unpredictable results. Okay, so now I'm going to show the experimental results we got from trying to prepare these phases on Aquila. First data point that I'm going to show has no local detuning, so we should see the same thing with both preparation protocols. The only difference is that there will be slight timing differences in the protocols, which will lead to minor differences. But we can see clearly if in the local first protocol that we have a clear DC version of the symmetric phase. The global first protocol doesn't work as well because we sort of prepare the phase and then we let it sit for a little bit, so it has time to decay. But you can still see that the DC sublattice has a higher density than the A sublattice. These are very different if we try to prepare the phase down here in the asymmetric phase, where we can see clearly that if we do the local first preparation, so we go down and then to the right, we get a nice asymmetric phase. But if we go global first and then local second, we pass through the phase transition and we wind up with this just homogeneous phase. So we wind up with two different phase diagrams, one calculated using local first protocol and one calculated with the global first protocol. And they show different things. There's one major caveat with these phase transitions, which is that the local detuning we used to calculate them or to construct them was a experimental capability at the time. So there's not very strong quantitative agreement between the local detuning and the experiment and the numerics. But qualitatively, we see the same thing, which is that if we do the local first protocol, we can very well prepare this A site symmetric phase. If we do the global first protocol, we can access the BC symmetric phase. And you can see clearly that there's this first order phase transition here in the data. So this is good preliminary evidence that we can access this type of water vapor transition as well on quantum hardware. I'm running out of time, so I'm going to go through this next section a little bit more quickly. This final experiment was an attempt to see the glassy dynamics that I talked about before. So we don't show this on the phase diagram, but we do have numerical evidence that there's something called a string phase that exists up here at this star point, extended above the phase diagram. And the details don't matter for now, but the important thing is that this string phase is very similar to the physics that they observed in the numerics for the highly entangled liquid phase on the Kagome lattice. So we have good reason to believe that this part of the phase diagram should exhibit the same glassy dynamics that were predicted for the Kagome lattice. The question is, how do we probe that numerically? So the idea is to start in the star phase, which we know very well and we can prepare well, and then to quench either into the disordered phase or into this string phase, and to compare the decay dynamics of the star order parameter after we wind up in these different phases. And what we should see is that when we go into the disordered phase, the star order parameter should decay very quickly because there's no reason that it shouldn't. And then what we want to see is that if we quench into the string phase, we want to see some evidence of this glassy dynamics. So we just want to see qualitatively that the decay of the star order parameter is different when we quench into these two different neighboring phases. Visually, what we're seeing here is the color corresponds to a local marker for the star order parameter, and the different squares are measuring that order parameter different amounts of time after the quench. So this is what the order parameter looks like before we do the quench. And then this is 15 microseconds after we go into the disordered phase, et cetera. And what we can see is that it basically disappears immediately. So there's very rapid exponential decay of the order parameter after this quench. But if we instead go into the string phase, you can see visually that the decay is much slower in the string phase. So that's good evidence for what we were hoping to see. This is easier to see if we instead just plot the star order parameter itself instead of this locally resolved version of it. In this plot, the x-axis is the time after the quench, so we measure the order parameter, and the green and blue circles are two different quenches into the disordered phase, and the star is the quench into the string phase. The important thing to see here is that for the disorder quench, we see very rapid exponential decay that quickly levels off to some constant minimum. But for the string quench, there's two things happening. There's this initial exponential decay, but rather than flattening out after that, it continues to decay at a much slower rate afterwards. And so this is a very recent result. We only got this a couple of weeks ago, but we think this is good preliminary evidence for observing the glassy dynamics that were predicted before in the numerics. Okay. That's the last thing I wanted to show you. So I'll just remind you some of the key takeaways from what I talked about today, which is mainly that I wanted to try to convince you that these Rydberg atom quantum simulators are a very powerful tool for studying many body physics. And we were able to, by studying the Lieb lattice, we were able to access some exotic multi-critical phenomenon that previous studies were not able to access. We were able to see a quantum water vapor transition, and we were able to get some hints of these emergent glassy dynamics. Thank you for your time.
Good question.
I was wondering, were you able to calculate the critical exponents for any of these transitions, either using DMRG or Aquila? And if you were, which one gave you better answers?
Yeah, so we were able to do some finite size scaling analysis for, was it this disordered to collinear or disordered to star transition? Do you remember, Milan?
Yeah, disordered to collinear and a little bit for water vapor as well.
Yeah, so we did some finite size scaling and got relatively good agreement with predicted critical exponents for those from DMRG. The system sizes on Aquila are just too small to get good agreement. We tried doing Kibble-Zurich, but we just couldn't see the universal scaling yet. The important difference here is that we basically have double the unit cell size that the previous experiments had with the square lattice. So it's harder to access critical dynamics or critical phenomena like that at the current, system sizes that we can do on the device.
So it might be a naive question, but are you creating these ground states by using adiabatic state prep?
Yes.
Okay.
Yeah, exactly.
And how do you reach the, how can you produce a ground state of a star phase? Because it looks like it's not reachable from either of the axes.
Yeah.
Have direct access to.
So this is a subtle thing. The important difference is that this star phase transition here is first order, but down here it's second order. And importantly, when you're doing adiabatic state prep, you can go through a second order transition without any problem. First order transitions are the ones that are difficult. So in this water vapor preparation, it was important that we studied which adiabatic path we were taking because it had a first order transition, but we can get into the star phase by just going through second order transitions. So the adiabatic state prep still works. That's a good question.
For a finite size system, the gap doesn't really to zero.
So it's not so much about the gap for these first order transitions as it is about whether or not there are intermediate metastable states. But I think what's happening with this water vapor transition, for example, is if we go through this first order transition here, what happens is that there's some homogeneous state that's like an intermediate like metastable state in the phase diagram between these two BC and A sublattice symmetric phases. And we're just getting stuck in it when we go through that first order transition, even if there isn't a gap closing. Oh, one more.
So all these lattices are basically square.
Yeah.
Variation. So that suggests that there's some fundamental reason why other forms. Can you comment on that just a little?
What exactly is your question?
Well, why is it always square?
Why is it always square? Well, I think we're starting with square sublattices just because they're simple. And the whole point of this was that we wanted to see what we get by using more complex lattices. And so the square sublattice or square lattice showed us some interesting physics. The Lieb lattice gave us more interesting physics. The difference between square and triangle, I think it's less clear what we would get by trying a triangular lattice. For example, the Kagome lattice has the same symmetry as a triangle lattice with sublattice decoration. But we can get to that by skewing the Lieb lattice. So it shouldn't be too drastically different. But yeah, it would be interesting to see what we can get on triangular lattices as well, since those have different properties. It's not something we've thought about in great detail yet.